Great. Okay, so I think we're all aligned in that we would like to build less artificial neural networks and somehow leverage their efficiency. And efficiency, I think, is the main reason. We often think about energy or power efficiency, but there are many other things that brains are just much more efficient at and allow us to do much more amazing things than driving cars. But yeah, humans are just very versatile. And obviously, there are biological neural networks powering this versatility. Now, because this is the beginning of the meeting, I thought I'd give a bit of an overview of work from my group, which focuses really on learning algorithms. So how do you get neural networks to do something? And most of the work is published, and I'll point it out as we go along. So I'll talk a little bit about spiking networks and how to train them in the beginning. And then I would like to get back to some more recent work that we've been looking into on local learning rules again and resurrecting them because I'd somehow in between given up on them. So if we think about one of the properties of brains, which is spiking, and then the question, if you want to put some intelligence in your chip, for instance, is how do you get a spiking neural network to do anything useful or intelligent? And I think in the age of deep learning, the go-to answer to this is that you want to do at least some form of end-to-end training or end-to-end learning. And I think this is mainly a recap of some very exciting work that has come out over the last 5 to 6 years or so, where essentially the community has rediscovered the fact that even a single spiking neuron is essentially a recurrent neural network simply because it has an internal state, which is the membrane potential. It might have synaptic variables and so forth that carry through time. And we've already heard it earlier in Bill's talk, where the state is important. So this was the realization that even a single spiking neuron is a recurrent neural network, meaning also networks of spiking neurons are recurrent neural networks. And the important news here is that there are known training algorithms such as backpropagation through time or real-time recurrent learning that can efficiently train these networks. And the big problem with this in the past was always that, of course, there's a spike somewhere here given by the Heaviside function. And if you take derivatives of a spike, and when you execute the chain rule in one of these recursive algorithms, means you're computing a product of derivatives, and one of these derivatives in this product will inevitably be now the derivative of a Heaviside function, which is 0 typically if you're below the membrane, the threshold, the firing threshold, or if you're at the threshold, it's infinite. So you have a factor that's 0 or infinite in the product, making the entire thing 0 or infinite. And that was always a problem for optimization, precluding end-to-end training. And I think, excitingly, one of the solutions that you can use are these surrogate gradients, and they've proven very successful empirically in training spiking neural networks. And the idea is really mind-numbingly simple, that whenever you compute gradients in this product of chain rules, when you encounter a Heaviside function, you replace it with something that has a more well-behaved derivative, and that works really well in practice. And we can now train all kinds of spiking neural networks, deep spiking neural networks on all kinds of tasks. And you've already seen a very impressive example on this super noisy imaging data and tracking this dot. So, but one thing that always bothered us in a way is that if you look at the loss landscape here of a spiking neural network, here, this is not a cartoon, but it's actually a 2D projection of the loss landscape of a spiking neural network. So it looks like one of these Minecraft landscapes. And if you now integrate now the surrogate gradient starting from the minimum somewhere into all directions, you can plot this, so to speak, a surrogate optimization landscape, and you can immediately see why this works, because this looks much more smooth than this Minecraft landscape. But the problem with this was always that we were lacking some good theory to understand what's actually going on, why these things work. So surrogate gradients are a heuristic, and so what Julia got interested in the lab is to understand what the underpinnings are, the theoretical underpinnings. And we went back to the literature. People have looked at single neurons for a long time and single spiking neurons, and realized that if you have a stochastic neuron with escape noise, for instance, as here shown on the right-hand side, I'm still struggling with, okay, here. So on the right-hand side, this is a stochastic neuron. It's responding over multiple trains to a ramping current, and you can see it spits out stochastic spike trains that you can for which you can compute an expectation value. And so in expectation value, this is actually a smooth response of which you can compute a derivative or a gradient, which is shown here in yellow. That's not true for the deterministic neuron, but you can, of course, now choose the surrogate derivative in such a way that it's the same as in the stochastic case. So we thought maybe the stochastic approach actually allows us to understand what's going on. So the problem with applying this to deep networks or multi-layer networks is that basically stochasticity breaks the chain rule, and you can understand it in this way, that typically the expectation value of a product of derivatives is not equal to a product of expectation values of derivatives. So that's usually not the case. And that's really the problem, in a sense, to come up with a theory. What else can you do? Well, you could look at finite differences, but we know that finite differences does not scale, and it produces high variance in stochastic networks. And the reason is that basically, you can think of a rollout of a spiking neural network with stochasticity as a decision tree, right? Every time step a neuron either decides to spike or not. It's a stochastic process, so there are many decisions being taken, and you go down a path of decisions in a very high-dimensional tree. Now, if you do finite differences, you would do one rollout, then change one parameter, do another rollout, and you might end up in very different branches in this type of setup. That adds even more variance. So it's not an option to do finite differences. But what we did find is actually by some mathematicians at MIT, this paper from 2 years ago, where they basically derive an optimal way of dealing with stochastic programs, and they call it stochastic automatic differentiation. And what Julia found is that this exactly actually applies to our setup of spiking neurons and surrogate gradients. And this exactly actually provides the missing theory. And the basic idea here is that you condition on one pass through the stochastic network. So you freeze the noise going through the network. You condition these expectation values on that path. And then this is actually the right thing to do to compute. And surrogate gradients really fall out of this framework. And they link now the surrogate derivative that we usually use to also the escape noise function. And within that framework now, deterministic networks are just a special case. So that's just a side. I think it's exciting, but let's move on now to some other work that actually involves some hardware. So if you want to use a spiking neural network and hardware to do something energy efficient, what you need is dedicated hardware, and then you get a host of new problems. As many of you might know, there's noise, and there might be heterogeneity or device mismatch. So one of the problems is device mismatch. You have a software model that works really well. You put it on a hardware system which has perhaps some manufacturing variability. You get mismatch, and then your nice accuracy drops to something worse. Now, of course, you can mitigate this through some costly calibration processes, and that's been known for a long time, or through in-the-loop learning. So we were wondering whether we can do this surrogate gradient stuff through in-the-loop learning on some real hardware. So we teamed up with people who actually know something about hardware. So we teamed up with Johannes' group, and the work was done by Benjamin and Sebastian. So we used their BrainScales 2 system, which has analog neurons and this crossbar array for memory. And these analog neurons, they of course do have some mismatch. So we used an in-the-loop training approach for these analog neurons, where we, for instance, feed in latency-coded MNIST digit in spikes. Then we run the forward pass on the chip. And thanks to smart foresight by Johannes and his team, they included ADCs on the system. So this actually lets us get the voltages of the neurons for this rollout. And then we developed some PyTorch code where we can take the actual voltages of the actual system and inject them in our off-chip code for learning. So we have a PyTorch model which has mismatch, but we're injecting the true voltages into this model and compute the surrogate gradients for that. And then if you repeat this turns out it works really well. So you get here, this is now a 3-layer network, input spikes, hidden layer spikes, very sparse output traces, and it classifies MNIST. So of course, a small network, but you get down to this 0 training error if you want. And you can do 80,000 of these little images per second with a batch size of 1, which is pretty cool, and I think it's very promising. Now, what about calibration or the self-calibration here of the surrogate gradient? When you get a chip from manufacturing, you get membrane potential time constants, synaptic time constants, and threshold values that are distributed according to these red curves here. Now, of course, Johannes and his team put calibration logic on board to actually mitigate this. If you do this, you get the blue curves. But we then used this logic to make the chip even worse than it was by basically adding random noise, and that gets you to the green curves. And then we measured parametrically varying the amount of noise. We measured how well it does, in this case on MNIST, and here you have test accuracy over the level of decalibration, and you see this is basically the effect is zilch. Yeah, so the learning calibrates the system very nicely. Whereas if you do weight transfer, even for the fully calibrated case, if you upload the weights from the software, you actually incur a loss. So I think to me, this is very telling. It's very promising that if we want to build such systems, we should really think about the learning algorithms to go with them and to live with them and run on these systems. And ultimately, if you want to use surrogate gradients, you should better allow them to have access to somehow the voltages. Now this was MNIST, but this also works on keyword classification or keyword task, only using 256 neurons, in this case up to 80% accuracy or so. Right, so here the take home is really that you would want these learning algorithms to be voltage aware, because then this can really self-calibrate away a lot of problems, which might allow you to also save on some real estate on your device for not having to integrate specific calibration logic. Of course, you have to now add the plasticity logic there. Right, so in everything I've shown you so far, training was still done offline or off chip, and it used backprop. So another major interest, I think, for many of us is to get away from backprop and to go on chip and online. So, and the reason is that backprop is difficult to implement on physical or neuromorphic systems, often due to non-locality in space and time. So a question that Axel, a postdoc in the lab, got interested in is how to train noisy physical networks without backprop. And this work is all based on work by Benjamin Scalier and Joshua Bengio on equilibrium propagation. So a quick recap on their work. The idea is that you have a dynamical system, so a network which is a dynamical system, meaning all the neurons in this network follow some energy function. So that if you give an input here, the network will follow this energy function and the activities will all relax to the minimum of the energy. Now, if the network is not trained, the output might not be what you want it to be, right? So if you want to do supervised training, now what you do in equilibrium propagation is you give an additional input to the output. Confusing, I know. But you give an additional input to the output, which nudges these output neurons now towards the activity you want it to have. And because it's an energy-based model, all the units here, this activity will trickle through now from the back end, if you want, of the network, and the network will find a new equilibrium, which is shown here over here as number 2. And the cool thing is now there's a little bit of math that you can write down a local learning rule where the neurons need to only know the pre and the postsynaptic activity during this nudged phase and the free phase. So nudge is where you give this additional target input, and free phase is where you don't have it. And then for a very weak nudge, which I'm going to call the limit of beta, which is beta is this nudging strength, in the limit of beta towards 0, so nudge towards 0, you actually recover the gradient of the loss. Yeah, so that's cool. So it's a bit like a contrastive learning rule if you want, and that's what you get. Now, principle all good, but what if you have now noise in your system, which can happen if you go ultra low power, and also it's known for the brain to have noise. Then this is not so nice anymore, because all of a sudden you're limited by this requirement of going to this infinitesimal small nudge. So that's what I'm plotting here. I'm plotting cosine similarity of the gradient with equilibrium propagation with the gradient obtained with backprop, just for comparison in this case. And you see for small beta, this goes to 1. Yeah, so perfect alignment. And in the no noise case, you can do that. But as soon as you have noise, this small nudge means there's a very small signal that gets washed out by noise. And then this limit kills you essentially, because now with noise, you can't do that anymore because this gets lost and you're losing to an optimum, which is now for a slightly larger nudge. And even on MNIST, this brings you up, in this case, 1%, right? So for small nudge, no learning. With a big nudge, you get learning, but you're losing already 1% on MNIST, which is used. So that's clearly not desirable. We don't want that. So to tackle this, we turned towards complex analysis. So that's when you, as a theorist, you don't know anymore what to do. You put the black magic hat on of complex analysis. And I'll just walk, this might be a bit quick, but essentially in complex analysis, there's one property which is called a Cauchy integral, which allows you to turn derivatives into closed path or curve integrals in the complex plane. So derivative in point A, you can basically integrate around this point in the complex plane on any kind of closed curve, and you get this derivative. So long story short, after some algebra and some math here, what you can get is the gradient of the loss as a local learning rule that essentially integrates over what we call neuronal oscillations along a closed path around the free equilibrium. So this is now a path in the complex plane, bear with me. And essentially what this amounts to is that we have to compute the gradient of the first Fourier, the gradient is equal to the first Fourier coefficient of this nonlinear neural oscillation. So what we've done is we've made this nudge, this beta, now a complex number, we're rotating it around this free equilibrium in the complex plane. And we integrate over it, and that gives gradient. So that's magic. And you can see here, this allows you to go to a much bigger nudge. So this is good. And also with noise, this rescues you now all of a sudden. So you can get very close to perfect, even in the noisy case. And you see on MNIST, there's no loss. It also allows you to do, to train much bigger models. And this was one of the first works to show that we can now use this equilibrium propagation to train a VGG-like network on ImageNet. And we basically get the same accuracy here as training it with backbone. So we're quite happy about this. So this work is published, and I won't talk about a follow-up paper that deals now with weight asymmetry that just got accepted at ICLR. But I will say a couple of words about the elephant in the room, which is we introduced the complex nudge, meaning we call this holomorphic equilibrium propagation because the entire network becomes a complex valued network. So all the neurons are complex valued. And ongoing work is to make it real again. And we already heard a little bit about traveling waves and oscillations, and that's the path we're taking. So right now, we can map these complex phases that we need to represent complex numbers on a carrier wave. So we're thinking something like a gamma cycle. And on top of that, we have to have this neuronal oscillation that's slower than this carrier, which would be, for instance, beta or something. And it needs to induce phase precession of this gamma. And then basically the job of the learning rule is to get rid of the beat frequency if you want. But stay tuned, this is ongoing work. But if it works, I think it's an exciting alternative to backprop. Good, so in the last 5 minutes or so, another piece of work, which really gets now at the question of training a network with local learning rules and without supervision. So in everything I've shown you so far, we use supervised learning because we know how to do it. But clearly that's undesirable if you want devices that you carry with you every day to learn. You don't always carry a huge set of labels with you. And there again, we turn to brain inspiration. And obviously the brain has to solve this. It gets a lot of highly entangled nonlinear data that lies on highly entangled nonlinear manifolds, like for instance, all possible images of cats and all possible images of dogs. They lie on this highly entangled manifolds so that you cannot linearly distinguish them, but we have deep sensory networks in the brain, like the ventral stream, that somehow make sense out of this, and through plasticity, magically create representations that allow us to identify things as cats and dogs. How do you get there? Well, the idea is plasticity does this. The problem is that the Hebbian plasticity that we know also well from neuroscience doesn't do very well on this task. And this, you can see this when we take, for instance, a convolutional neural network, and we put a Hebbian learning rule inside, and we let it run with that. And we expose it to SciFAR or STL10 or a data set that you like. And then we assess how well this network learns to separate classes like cats and dogs by looking at the hidden layer representations at different stages. That's what's shown here. So there's a function of depth. And then we just train a linear classifier to assess how well are these things separate. And you can see it doesn't do very well. And we know the problem here is the learning rule and not the network architecture, because if we train the same network using supervised learning, it actually can solve this task. So what's going on and how can we remedy this problem? And the idea is prediction. So I'm fully aligned with what Terry was saying earlier. But the brain doesn't really need to reconstruct, doesn't need to learn a generative model necessarily of your input pixels. So you want to do prediction in latent space. And that's what I'm trying to show here. So this is the latent space. It's the output of some deep sensory networks. And prediction in this space now would amount to trying to pull together representations of things that appear close in time, right? So I'm looking at you now. I'm still looking at you. You're still here. So somehow my brain might predict that you're there and have an internal model of that everybody is here. And now if you were all replaced by zebras, there would be somehow a mismatch in my brain. And then I could adapt to this model, to this learning signal. The problem is if you just have a pulling force on your representations in this latent space, what usually happens is what's called representational collapse. What's perfectly predictable in my internal representation is that everything gets mapped into the same point. And the same point is perfectly predictable, but it's also perfectly useless. Good. So what's obviously clear is that you need some kind of pushing force that keeps things separate, that are separate. And good thing is, one thing that provides such a pushing force could be variance, so maximizing variance, or entropy in this representation space. How much time do I have left? Because you're standing up. Oh, okay. I thought I had 25. According to my watch, 3 more minutes, but okay. So maximizing variance prevents collapse. And so we've known for 40 years or so that you can actually derive Hebbian learning rules from variance or entropy maximization principles. So our idea was, well, if Hebbian plasticity doesn't work, but it actually prevents collapse, let's combine the two. And that now starts working. So here I'm showing you the same network. We're showing you videos of this procedurally generated objects. And if you now try to classify what type of objects were in this video, you can do this with high accuracy, whereas Hebbian only or initialization only doesn't allow you to do this. Now, again, in the interest of time, I'll speed up a bit. We can do the same thing with augmented images of objects. And lo and behold, this does really well. So that actually starts disentangling with depth these object identities. And last but not least, we can use the ideas of surrogate gradients to write down a spiking learning rule. Here I only have a small toy model with inhibitory plasticity for decorrelation. Get some input spike trains that oscillate, so making them predictable. And this is basically turning into a slow feature analysis detector if you want. Here is the activity of a spiking network after 10 hours of watching this. Here, these are the inhibitory neurons. If we try to reconstruct the input signals, we can only reconstruct the input signals of these slowly varying inputs. And we can see why, because the network chooses in its weights here to only represent these slow inputs. Good. And again, if we switch off the predictive term, all of this goes away. Good. So that's what I wanted to show you. We can do online learning with local rules and without supervision. Of course, we can improve here. These are the works that I've shown you today. And I think if we want to build more efficient learning for edge AI or for other applications, I think what we should focus on is lightweight online learning rules. They must be robust to noise, heterogeneity, no backdrop, please. And we should focus on algorithms that have a theoretical motivation, like, for instance, what I've shown you, holomorphic equilibrium propagation, but they must be practical, obviously, and not complex. And we should close the gap between self-supervised and supervised learning. And I think for that, we need joint efforts between the hardware and the software or algorithms developers. And that's why I'm excited to be here. With this, I'd like to say thanks to the team and my collaborators, specifically Johannes, Benjamin, Sebastian, Manu, Julia, and Axel. And yeah, thanks for listening.